Anybody got any questions before we start?
Number 14, 15, 16, and 20 on the study guide.
Oh, I don't remember those.
It's the. I didn't write down the questions. I was getting confused on the math. I didn't want to write it down wrong. To evaluate P of X and J of X T for e to the IKX minus MX.
Oh, okay.
And then J of X for the superposition.
So you're talking about the practice test?
The study guide.
Study guide. That sounds similar to the questions that are on the practice test. Right?
Yeah, I think they're the same questions. But I don't know if the superpositions on the, the superposition does not look like it's on the practice test.
There's a, okay, yeah.
Wait, what's their standard practice? Study guide?
Practice test is a little more specific preparation for the test. Study guide is a little more general.
I didn't see that.
I was getting confused with the math and I didn't want to do it wrong and then.
Yeah, that's what it goes wrong.
Oh man, it's really hard.
Okay, so let's see, we're continuing with our practice test. I think we're down to number 10 on the practice test. Any takers? Any takers? Come up. Good.
All parts or just, you want me to do them all?
Well, maybe just write down your answers and then we can talk about how you got them.
He wants to solve for them.
Yeah. Solve for it.
I mean, like solve for them on the board.
Well, let's see how it goes. Okay. All right. So, how do we get these answers from? So she wrote down the probability. How did you get the probability?
Size for size.
Right. And
G
psi
of
is,
X times the complex tangent.
yeah, psi is real, so it's just psi squared in this case. And so this is just the square of psi. Okay, that step. Everybody okay getting to that step? And then how about the average? Like average of X and average of X squared. How do you do that?
The integral of X times P of X times dx. Or just look at the graph for the mean of X.
Yeah, that's right. You can guess that this one is 0. Okay, so I'm going to give you a table of integrals. And for this particular problem, the table, put this down. In the table, there is an integral. A root I. There are 3 integrals on the table that you can use. Okay, so all right, so the A here, remember, you have to get used to having fluidity of symbols, right? Symbols are, they just point to something. In this case, A points to a generic number. So variables like these in mathematics, the way we're using them, they're symbols that point to something else. They don't have any intrinsic meaning. A has no intrinsic meaning, except as a symbol that points to a generic number. And so it's, in that sense, like a stop sign, right? Stop sign doesn't have any generic meaning as a sign. There are things that are physical signs that connect to the thing itself, to something. So the sky is illuminated, but the sign the sun is up. Right? Or you sit down in a chair and it's warm. It's a sign that somebody else is sitting there before you, right? These things are signs, real signs that connect you to something. These don't have that kind of meaning. These are signs that are pointing to something else, have no intrinsic meaning themselves, except in this case, they're pointing to a generic number. Okay, so you have to be able to make the connection here that to do the integral of this p here, you have to identify that a squared is 2 sigma naught squared, or a is root 2 sigma naught. And then you can use integrals like this. So in this case, in all three cases, we would say a is root 2 sigma naught. And then everywhere there's an a here, in the answer you would place root 2 sigma naught. This one is trivial because the probability density is symmetrical around the origin, so the average is 0. So this one, everywhere for the average of x squared, on probability, integral, so we have a cubed, or a is this. Let's see, a cubed, I'm sorry, a cubed. 2 times root pi, and then you simplify. Okay. Stay here. Square. Yeah, this is square. This is typo. Should be able to check the dimensionality of your answers, right? The dimensionality of the average of x. Well, it's trivial, so let's look at the dimensionality of average of x squared. Well, that's just the same as the dimensionality of x squared itself. And x. This wave function, x points to a length, location of the electron someplace in the range. This should be a length squared. Look over here as well to see, find the dimensionality of sigma naught. What's the dimensionality of sigma naught? Length. Yeah, it must be a length. In order that this argument of the exponential has a dimension less. X has a length, so sigma naught must be a length. Probability is a problem. This is really a probability density. I think it's calling it probability. I should say the correct. It's probability density. So it's there's an inverse length here up front. Probability density is probability, the number per unit length. Everybody okay? All that. And what should be the probability? I'm sorry, the dimensionality of sigma x. It should be the dimensionality of x. Get certain x. So that should be a length. So the Gaussian probability, the Gaussian wave function, and the Gaussian probability density from that. What was I going to say about that? Okay, so this has a parameter in it, and this parameter is chosen so that this integral gives sigma naught squared. Okay, so that's why we have a 2 sigma naught squared here, so that the standard deviation equals sigma naught. But the standard deviation for a general probability distribution, we'll call it sigma, but it's the standard deviation, but it doesn't correspond necessarily to some aspect of the curve. So if we plot the Gaussian, sigma is the place where the curve, there's an inflection, right, for the Gaussian. That's not true for a general probability distribution. You might not have an inflection, right? You just have the standard deviation. It's some measure of the width probability.
What do you mean by inflection?
Where the curvature is 0, right?
Oh,
Here it's got a negative curvature, on here it has a positive curvature, where the curvature is 0. So you take the second derivative of this and set it to 0. That occurs at x equals negative sigma plus sigma. So for a bell curve, the sigma corresponds to the inflection. in the probability distribution. That's not generally true for probability distributions, but with standard deviation may not match a feature like the curvature goes to 0 in the probability. Any questions about that? Yes.
Wait, so did you say that, so standard deviation doesn't always match up with where the curvature changes?
Correct.
But the probability does here?
Yeah, it just happens to because it's a Gaussian.
Okay.
Gaussian is kind of it's kind of an iconic probability distribution, right? So we're often drawing a Gaussian when in general we mean a probability distribution. But you can have other probability distributions. So for example, let's suppose, go back to the coin toss problem. We have an ensemble, each member has a single coin. Pass it out, everybody flips the coin, comes back to the answer. Let's assign tails to -1, heads to +1. What does the probability distribution for the ensemble look like?
Theoretically, I guess.
No, not a Gaussian, 2 delta functions, right? You either get +1 or -1, right? So the probability distribution would look like this: 2 delta functions, a magnitude half at -1, and another half of the ensemble comes out at +1. It's not a smooth curve. There's no inflection point to the distribution, but there is a standard deviation. What would be the standard deviation of this? 1. So in fact, it would come out as minus sigma plus sigma is where the delta functions are. Right? But you could have another distribution. Suppose you have a coin with, a die, six-sided die. You assign 1, 2, 3, 4, 5, 6, right? So give me the number that you get back. What does that probability distribution look like? So you have 1/6 at each of the integers up to 6. 1, 2, 3, 4, 5, 6, and they're each of equal weight 1/6. What's the average? Well, it'll be between 3.5. What's the standard deviation? It'll be somewhere around like this, 1 or 2. Deviation, I don't know exactly, but it won't correspond to a particular feature here in the probability. Does that make sense? So we call it uncertainty, standard deviation that's defined specifically as the square root of x squared minus the square root of f captured x. May not correspond to some particular feature in the probability distribution. For the Gaussian, it does. Just don't be confused by using sigma in both places, right? We say sigma here. Virtually everybody writes sigma in a Gaussian probability. But it is the standard deviation. Okay. What's the next one? Evaluate the probability density for a plane wave. A plane wave, right? Plane wave solution is the name of that. So pure mode for a free particle. What's the probability density for that? Two cosine or cosine? No. 1. So anything of this form, e to the I x, e to the I theta, and e to the minus I theta is just 1.
Oh, yeah, sine squared cosine.
And just in polar form, remember you just add the exponents. Do it in polar form. Don't convert to Cartesian form. Just do it in terms of exponentials. Straight in polar form. All right, here's another longer one. For this, calculate J, and I gave you at the top the form for J. Anybody like to work through that one? Find J for this. And what is the meaning of J? probability, current density.
Probability.
And the charge current density, which you saw in electrodynamics. Probability current. I wrote it at the top of the practice test.
Software right now.
Volunteer,
You want me to write the answer? I don't have the answer, but I can solve for it.
go ahead. Okay, remember that the Broglie relation is written in a little bit different form here. H bar K is the same as H over lambda. That's the momentum divided by the mass. Right, and the probability is 1. So this is just the velocity. The probability is 1/6 the velocity. In general, the current is the probability times the velocity. Probability here is just 1. So, okay, a few questions. What is the meaning of this? Velocity.
It's the average velocity of the ensemble.
Yeah, remember, always think in terms of ensemble. Average velocity. Now, this is possibly a function of x and t because psi is a function of x and t. So it's actually the velocity, the average velocity of those particles that are x at time t. And because the probability is uniform and the current density is uniform, looks like it's just the same for everybody. It is the same for everybody in this case. So this is an ensemble average. It's the same at all values of x. Okay, just a little hint about how to do math a little bit more efficiently. I would often decide, or somewhere else, right? Decide by dx is ik psi, right? Use the ikx times omega t, and write it as ik times psi. Instead of doing a substitution straight away to get the full expression, take a piece of the value. Then when you do this, you can see it's psi star psi times ik, right? That first term. You've already evaluated psi star psi. And notice that this is the complex conjugate of this. You don't actually have to evaluate it, you just take the complex conjugate of the thing you just evaluated. Okay, so this is going to be plus, and then we get psi star minus ik. That should be minus here, right? Psi star psi, psi star psi, psi star, it's the same, that's just one. So that saves a little bit of work, right? Because you keep writing down all this exponential stuff, the more you write down, the more likely you're going to make a mistake. So try to simplify, be strategic about what you're doing. It'll help when you're dealing with a lot of terms. It's not particularly hard. Yes, sir.
So the complex conjugate of a function, like the derivative of the complex conjugate of a function is same thing as saying derivative of the function is the complex conjugate after you find the derivative.
So once you take the derivative with respect to, careful. In this case, x, the answer is yes. But if you take the derivative with respect to a complex number, complex variable, you have to take the derivative, you have to take complex conjugate, so you need to be careful. In this case, yes.
That's not a common property of the complex conjugate. It's not a property of the complex conjugate that it can work in and out like that. That's just this case. The complex conjugate of the derivative of a function is the same thing as saying the derivative of a function. The derivative of the complex conjugate of that function.
Only if x, only if the thing you're taking the derivative with respect to is real.
Only if it's real.
Only if the thing you're taking the derivative with respect to is real.
So not just complex.
I think, if I understand your question.
Yes, sir. That's what I was trying to understand right there is what you did there.
Yeah, because x is real. I can, this complex conjugate of this is this. Because x is real, otherwise I have to take a complex conjugate of the thing you're taking.
Oh, if you're taking a derivative with respect of something, if that derivative you take respect to must be a real number in order for that complex.
In order for this expression to be complex conjugate of each other. If
Okay.
x is real, then yes.
But if it's a complex, you couldn't say that.
Right.
Okay.
Okay. Let's see. Down here. Okay, so the question 13, I guess I'm reading it. What I should say here specifically is how to calculate average of p squared, and sigma p directly from the wave function, right? What I'm getting at here is that you don't have to go through the Fourier transform to get the average value of p squared. So in general, you have some wave function, find x p, how to go directly from that without going through Fourier transform. These things. Somebody write it for me. Somebody hasn't had a chance yet. Yeah, Silva, come on.
Can I bring this?
Sure. You'll need to be able to do it without that. Okay.
by mixing up symbols.
What's that? I'll keep in mind p hat. Okay, but now you've written it as integral over k. Right, it's an integral over x.
Oh, it's not go over that.
Over x, yeah, because psi is a function of x. Doing it directly in as functions of x. Going through Fourier.
Can you square that?
Yeah. Questions about that?
The reason why that works is because generally the average is the integral from like x of the probability density, right? The x, right? Infinite integral, right? So you do p hat, it pulls out p. You do p hat of psi, it gives you p times psi, right? So it's like the same thing.
No, it doesn't give you p times psi necessarily. It does for a plane wave, but not in general. So it's not true. This is not true in general. It is true for a plane wave, but not true in general.
So how can you?
Yeah, we went through that. That's on page, right? That's in the book. You gotta go through that. Covered that, so that's something you need to review. This is not true. It's true for a plane wave. Right, let's try that. Let's put in for a plane wave e to the I kx minus omega t. Let's apply this operator. This is the key here. Mr. Silver wrote down the momentum operator or wave function of x and t. So this is minus I h bar d by dx. Okay, let's apply that operator to the plane. Derivative brings down a factor of ik. And these combination of signs here gives h bar k times the plane. This is p. That's true, but that's the only case where it's true. Let's take a Gaussian, for example. Let's go back to the Gaussian wave function. Can I erase this? Let's try it before, so I'll write it down. P times. So that's true for a plane wave. But let's take, for instance, a Gaussian. We have all kinds of constants, but the main thing is we have that part that depends on x. So we get minus I h bar, we get minus x over sigma naught squared times the Gaussian. Okay, so cleaning it up a little bit, you get h bar x over sigma naught squared, I h bar x over sigma naught squared, minus not p times the Gaussian. So we'll talk more about that in the next chapter. About this kind of an equation. In general, that's not true. The proof for this is when we went through the Fourier transform. If you substitute the transform for psi here, and then through this operation, you'll see you get to the average value of p relating to the Fourier transform. That is the average value of p in terms of the Fourier transform. This is the probability of having p. Integrate p times that probability over p. That gives you the average of p. Okay, but there's a direct route without having to go through the Fourier transform. This gives the same as this. For you to see the detail, you need to work on that. It's on page 90, I think, something like that. Under text goes through the derivation, several steps, but it's all in one place. Okay, but you don't have to go through all that work. You can go straight from psi. Yes, sir.
And the P hat, you can do that, you could switch the signs, psi star, correct?
Ah, you mean, put psi, p hat psi star.
Yes.
Doesn't work well. Let's see, hang on.
Would there be a sign?
There's a sign change. Yeah, that's right. And so, hold on to that thought just a minute. Everybody okay with understanding this? The idea is you can go directly from psi without going through the Fourier transform. It's working. But in principle, it gives the same answer. But it doesn't apply, you're just applying p hat onto this, you're going to get a number, p, on psi. It doesn't work like that. Okay, can I erase this? Everybody see the counter example?
Yeah, first one. So because it only works for plane waves, we cannot say that I h bar x over sigma naught squared. That's not P, correct?
Correct.
And the reason why we can do that is because the average. Never mind.
So in general, for if we have something that can be measured, call it A, some generic thing like X or P or energy or something, we can measure something. There will be associated with that an operator in quantum mechanics, which can operate on the wave function to extract that, so that the ensemble average of that measure is going to be given by psi star a hat psi. And the question of whether you can revert the order here, put it psi, something else here, psi star, we're going to consider what kind of operators, where if sign change or not. But so you could define the operator that if I switch the order psi a hat psi star, there would be an operator associated with that.
For the lens that we're looking at right now, it's better just to
Yeah,
memorize that.
this is a standard way. Everybody does it this way. Just so you know the standard, and then you can start trying to understand why it's the standard. Okay, so in this case, for momentum, this is the operator. For the energy, there's an operator called the Hamiltonian. Sometimes it's the energy, depends on the Hamiltonian. If there is an energy, it's this combination of kinetic energy and potential operators. Kinetic energy is p squared over 2m. Potential energy is just easy. It's a function of x, just multiply the wave function by p of x. Whatever it's on. Okay, and so Mr. Silva was asking, can you square it? Well, yeah, you just take the square of this is then the second derivative, right? P squared is going to be minus h bar squared times the second derivative. You just square this, second derivative doesn't act on the constant, so this just pass through to the left. The second derivative. So the general rule is going to be this. What we're learning is that we can find an operator that's associated with whatever measurement that you're making that will help you to form then ensemble averages of that measure. And also the sigma. Right? We can do average of a squared. Square that operator, whatever that gives. And then there's a standard deviation associated with that measure. the general pattern here. But we're able to extract things, but it always has to do with ensemble measurement. There's an operator associated with the wave function. So this is a new way of doing dynamics, a new way of understanding how things are changing in time, like having operators that extract things from the wave function. That's what it's all about now. That's the mathematical machine that we have quantum. Okay, let's see, number 14, right away function, that's a superposition of the two lowest states for the particle in the box. So volunteer. Maybe face the volunteer early. Easier question. Okay, so we need to know the particle in the box states, right? So in general, though, it's there. That's the general expression for any superposition of just two terms. These are the particle in the box states. These are of the form a spatial part and a turbo time dependence. They have different frequency. In general, they do have different frequency. Okay, so the particle in the box have those memorized. Particle in the box. And the frequency associated with each one. I think we did this right? I generally try to write problems so that there's not too many pieces to each problem. I may have a question at the beginning to write down the particle in the box states, and then maybe a question later says use those forms of position, right? Instead of giving you one question which has both in it, so that you can show the piece you understand. Questions about this? This is a stationary state. No, why not?
Superpositions are never stationary states.
They can be.
Really?
Yeah. Turbos are always stationary. What would be a condition where this would turn out to be stationary? So what do we mean by stationary?
The time.
To the probability, not to the wave function, but to the probability. Suppose omega 1 and omega 2 are the same. They aren't in this case, but suppose they were. Then the time dependence would cancel out of the whole thing. Right? The time dependence to the probability depends on the difference between these two frequencies. So for the particle in a box, it would. But if these two frequencies were the same, which is possible, and in higher dimensions, we're going to now do more things other than just one dimension. If you have two states that are the same frequency, which you can have in general, then the probability distribution is stationary. Yes, sir.
With this, since it's because this is still pure mode since it's the n squared, right?
These are pure modes.
All right. So since those are pure modes, is it just the different magnitudes of frequencies that makes it a superposition?
Yes, all right. Yeah, the fact that the frequencies are different. No, I'm sorry. That's not right. I think I answered your question incorrectly. It's a superposition not because the frequencies are different, but because they're different pure modes. In other words, you can have pure modes at the same frequency, but they're different pure modes. So it is possible. That's called a degeneracy. For example, in the hydrogen atom, you might be familiar with the p state. There's 3 p states. They all have the same energy. So you could have a superposition of 2 of the p states, but that would still be a stationary state. Kind of unusual, but it does happen. We have degeneracies. We have pure modes, more than one pure mode at the same frequency. And if you form a superposition, that would be a stationary state. We'll get to it. We haven't done it yet. We're coming to it when we do the hydrogen atom. In one dimension, it's unusual to have degenerate states. It's not unusual to have degenerate states in higher dimensions, 2 and 3 dimensions. That's the usual thing. Okay, how are we? Let's see here. Okay, the last one is the canard uncertainty principle. To explain that fully, what I mean by that is all the essential parts. Explain the meaning of that equation. Canard uncertainty principle. Okay, how would you do it? You don't have to come up and write it. You can just say it in words. We'd like to give it a go. This is important. Yeah, go ahead, Ms. Morris.
It is 2 very different ensembles. Take one sample, divide it into 2. So you're not doing the same measurement twice on any one thing. One ensemble, you do position. The totally different ensemble, you do momentum. Then there's a relation of sigma x times sigma p is greater than or equal to h bar of 2 to describe the relationship between the uncertainties and the measurements of the entire of the ensemble.
That's very good. The only thing I would pick at is you said 2 very different, 2 completely different ensembles. And there's the problem with that is that it may sound like you're preparing it from 2 different states. So it's better to say you start with one ensemble and divide it in half at random, because both halves are being prepared in the same way. Say they're 2 different ensembles, you might be thinking this leaves it ambiguous about that fact that they all have to be drawn from the same preparation. Right. Yeah, Mr. Green.
Prepared in stateside.
Yeah, that's right. There's one state that's described by psi. Psi describes the quantum state. There's one state, so you take the preparation, the ensemble that's prepared that way, and divide it into half. There's no, you can say at random within that, but there's no difference between the 2 halves. She said from 2 entirely different ensembles makes it sound like the 2 halves are possibly different from each other, but they're not. They're only different by a matter of choice. I happen to choose these guys and these guys. And on this half, I'm going to measure x squared as well. Get a sigma x. Here I'm going to make measurements of p. I form an average of p squared, get sigma p. The product has a lower bound, regardless of the original state that you prepared it in. So this is true for any state. If I do this, I'm going to get product is going to be greater than p4/2, greater than or equal. The one case where that's equal is the Gaussian probability distribution, Gaussian wave function, as that beats the lower bound. It's equality. I think all the other ones that I know about are above p4/2. Okay. Any questions about the practice test?
Or what?
What's that?
By other. Said at the very end. Others.
We've had other probability distributions, right? As far as I know, all of the other probability distributions that we've considered would not, and in fact, anyone that I know of, it's greater than, it doesn't meet the equality.
It's the canard uncertainty principle. That's just generically, that's like generically it's not just true for, that's like mathematically true when you look at statistics, but that's like applied quant, right? In our part.
No, there is an analogous theorem for Fourier transforms. Is that what you're asking?
I'm unaware of that.
Okay, so I don't understand the question.
I was just saying like the sigma sub x times sigma sub p is greater than equal to.
That's a physical theorem. It's a theorem that applies physically to physical systems.
Oh, so it doesn't just have to, so it must be position, it must be the measure of momentum. It can't be like on the temperature or something, you measure the temperature at that time. This guy measured the temperature, like, that you have 100 ensemble, you have 100 people in the ensemble, 50 people take their own, they measure the same position, 50 people measure the temperature.
No, it's just X and P. Although there are other pairs of variables where there's a similar theorem, an uncertainty principle. There are other pairs of variables. Okay. So the first pair we've encountered is X and P. Remember, X and P have special relationships. Right? P is a measure of the impetus. Impetus is the cause of the change of position. Right? So there's a special relationship between those two. So we'll consider in the next chapter other possibilities between other combinations of variables, but they have to have that special relationship between each other for this to be true, for something like it to be true. Okay, so let's see. I wanted to show you. Well, wanted to talk while I'm waiting for that. Just generally to help you with your understanding about why I like this textbook so much. You understand the distinction between description and an explanation? Can somebody give me an example of each? Yeah, Mr. Silver.
You can like describe like a color or a picture or something, but like to explain it is a lot harder to do. I would say.
You understand a lot more, don't you, to be able to explain it? I can talk about, describe what just happened. Or I can explain it, which is what you learn how to do at the beginning of the semester in terms of impetus, force, change of place, mass, principles of locomotion. The principles, to understand the principles, really understand the thing. So providing an explanation is when you get to the principles, get to the essence of the thing, understood in terms of principles, provide an explanation. That's really what this textbook is trying to do, is to help you to understand the explanation, provide the explanation in terms of basic principles of physics, rather than just having a description. So that's the focus of equation only tends to be descriptive, whereas understanding the underlying causes helps you to explain. This is really where science is. Description is a part of that. You often begin with a description, but you don't end with a description. Just ending with a description is leaving you in the lurch. It's like, okay, here's the description. I don't understand why I did that. Okay. Okay, so that's good for today. So there's a test in class on Wednesday. And I'll provide you with a table of transforms, table of integrals, even the expression for the current density, like it's in the practice test. So you shouldn't need anything except paper and pencil. So we'll see you on Wednesday.